Okay, so the other day we learned about basically network, right? That was kind of the big thing that we learned about the other day, was this idea that if you find the network, in other words, the work done by your net force, or the total of all your individual works, then your work net is equal to your change in kinetic energy, right? Okay? So today, we're going to learn about one very specific type of work, which is work done by gravity. All right? In a lot of ways, it's kind of silly that this is a whole section, because it's going to be very closely tied to, when we get to Chapter 8, we're going to learn about gravitational potential energy, and they're very, very closely related. Okay? So again, as I said on Friday, I know it's a little weird, but as much as you can, try to forget about potential energy until we get to the Chapter 8 stuff. And I struggle with it too, because it's so natural to think about that, especially when I know you guys solved a lot of problems in the last year. All right? Okay, so when we calculate the work done by gravity, you do it the same way that you would calculate the work done by any kind of force. It's force dot distance, okay? So for us, the work done by gravity would just be equal to the force of gravity as a vector, dot product with the displacement, okay? And then dot product can be written as, force of gravity times the distance times the cosine of the angle. So remember, this theta is the angle between your force vector and your displacement vector. Cool? All right. And then we'll do an example where this will be made more explicit, but it turns out that d cosine theta just gives you your vertical displacement. Okay? And you'll see that in an example. And then force of gravity is just negative mg, right? Okay, so we saw in examples on Friday that if your object was moving one way and the force was sort of contributing to motion in that direction, that you'd get positive work, right? Because you'd be gaining kinetic energy. Does that make sense? Whereas if your object is moving this way and the force is sort of working against it, then you get a negative amount of work, right? Because you're going to lose kinetic energy. Follow? All right. So in this example, it's pretty straightforward. Gravity always points down, right? So if your object is moving down and the force of gravity is down, then you're going to gain kinetic energy, right? So that's positive work. Okay? So that's what this says. So if the object oh, sorry, I forgot what my graphic meant. Sorry, give me 1 second here so we can fit this whole thing on here. All right, yeah, this graphic actually tells us a lot. Okay, so let me pause and say this again. So if the object is moving down, then gravity pulls down. The object is moving down. You're going to gain kinetic energy, so that's positive work. It's done by gravity. Good? If the object is moving up, it's the opposite, right? Gravity's down, motion is up, so gravity's working against the motion, so you'd be losing kinetic energy, right? So that's negative work. Good? Okay, so that's kind of what this graphic shows. But there's some extra information too, because they've got this extra force F. So that's, whatever, some applied force. So in this first example, you've got some applied force upwards, and the object is moving upward, right? See, it says upward displacement. So in this example, my force here is doing positive work, because it's in the same direction as the motion. Whereas gravity is doing negative work, right? Because it's moving up, but gravity is working against it. Okay? And then here we get the opposite scenario, where it's moving down. So then gravity is doing positive work, and the upward applied force is doing negative work. It's a lot to wrap your head around. Did that all make sense? Are we good? Okay. I'll tell you, more often than not, as I've been solving these problems, I really haven't used this equation a ton. I've done a lot of finding components of vectors, and then just thinking about if the force and displacement are helping each other or working against each other. You know what I mean? And I think that sort of intuitive sense is going to serve you better than just trying to remember this FD cosine theta thing. Good? Okay, so. All right, so what we're going to do is just kind of run through some different examples for a box that's moving up and down, okay? And sort of either going with or against gravity, okay? So, in this first example, we've got a 5 kilogram box that's falling down 4 meters. So, to set this up. All right, so let's start just by going with the equation, okay? So the work done by gravity in this example would just be the force of gravity dotted with your displacement vector, right? I guess I should put little arrows over here, right? So everybody point for me. This is silly, but bear with me. Which way is gravity pointing? Straight down, right? Which way is the box falling? Straight down. They're parallel, right? So I just know that they're both going in the same direction, right? So my force of gravity is going to be 5 times 9.8, right? I guess I should put units on this. Okay, so my net force is downward, right? And then the displacement's parallel, so I don't even need to worry about the cosine of theta, right? Because it's cosine of 0. But it is down, so that's negative also. Cool? In the end, you just need to be thinking, oh, it's both the force and the displacement are down, so my work is going to be positive. And just make sure, ensure that that happens. All right, so multiply this out, and you get 196 joules. Good? All right. Now, if it's falling, then gravity's our only force, right? Does that make sense? All right, now it doesn't say it explicitly, but if we assume that our initial velocity is 0, then that means that our initial kinetic energy is going to be 0, right? So what should our final kinetic energy be? 196, right? Because work is change in kinetic energy, right? So my work net is equal to my work done by gravity, which is equal to my change in kinetic energy. So my kinetic energy final, we haven't used a lot of, I guess I'll just put K instead of final, because we've been using KO and K, right? Does that make sense? Okay. And so then you can find the velocity, right? So remember, V was 2K over M square root. All right, and if you solve for that, velocity, you end up getting 8.85, I think? Yeah, 8.85 meters a second. Sorry, I kind of squashed in there. All right, positive or negative? Negative because it's moving down. Okay.
That's the velocity at after 4 meters.
Correct. Yep, and that's exactly what I was going to ask next. So is everybody good with that? Okay, so I said a minute ago that this was really closely related to gravitational potential energy. Do you guys remember the equation for gravitational potential energy? Anybody? MGH? Does MGH ring a bell? Check it out. MGH. Right? So,
Rocket science.
yeah, so in a chapter, we're going to learn the equation for gravitational potential energy, and there it is. All right? Okay, so are we good with this? Okay, so now this next example is almost the exact same thing, except this time instead of dropping our object down 4 meters, we're going to throw it up into the air 4 meters. So calculation-wise, what's going to happen is this. Now my work done by gravity is still, well, my force of gravity is still the same thing, right? But my displacement is different now. What's my displacement now? Oh, okay. So to be clear, when we talk about it being thrown 4 meters straight up in the air, we're talking about the work done by gravity between the instant that it's thrown and it getting to the top of the path. Okay? So, but yeah, so the displacement's going to be positive 4 meters, right? Right? So now the work done by gravity is negative 196 joules, right? Which makes sense, because as it goes up, it's going to lose 196 joules of kinetic energy, right? Follow? So that means we must have started with a kinetic energy of 196. So we started with a velocity of 8.85, and then the velocity decreased up to 0. Decreased up to 0, I said that badly, but you know what I mean. Cool? All right, any questions with this? All right, so I think the big thing to note here is, so in the first example, the work done by gravity is positive, so we gain kinetic energy. In the second example, the work done by gravity is negative, so we lose kinetic energy. Cool? Any problems? You guys okay, Christian and Ethan? Say that again. Oh, if you did FD cosine theta. So, yeah. So when you use the, and this is what Alex was asking about before. When you use that, when you use work equals FD cosine theta, these are understood to be the magnitudes of the vectors. So there's no negative signs. So you'd have a positive force, positive displacement, and then cosine of 180 is negative 1. Cool? Correct. Well, here it is, because that's dot product by definition. Good? All right. Are we good or no? I feel like I'm not doing a great job with how to explain when there's positives and negatives. Are we okay? Okay. All right. I'll make myself a note, though, so that I can think about that a little bit more. All right, so we're good? All right, now. So this time, instead of having the object just drop down 4 meters, we're going to have it go down a slide. It's still going to go down 4 meters, but it's going to go down a slide. All right? So if you want, sort of off to the side, it might be worth your while to make a little drawing here. So here's our ramp. It's inclined at an angle of 30 degrees. It's 8 meters long. If you do the trig, this guy ends up being 4 meters. All right, so I'm hoping that this will help you see that there are kind of different ways that you can calculate the work here, and they all amount to the same thing. Okay? So, work done by gravity. So, I tell you what, let's do it just straight by using the equation. All right? So, if we do the work done by gravity, if we write it this way, if we write it as Fg times d times cosine of theta, then my Fg is still going to be, let's see, it's going to be 5.0 kilograms times, sorry, I started to put that negative in there out of habit, times 9.8 meters a second squared. So that's my force of gravity, right? Now, as it slides down the ramp, what's the displacement going to be? I heard both 8 and 4. Your ramp is going, the box is going to go down the ramp from here to here. So what's the displacement going to be? 8 meters, right? 8 meters. All right. And then times the cosine of theta. But be careful. Theta is not 30 degrees. Why? Well, let's see. Everybody point for me. Which way is the force of gravity going? Force of gravity. Which way is my displacement? That way. Here's my angle. Follow? So what's that angle going to be? 60 degrees. Cosine of 60 is? Cosine of 60 is a half, right? So we're going to get 5 times 9.8 times half of 8. We get the same answer we got before, right? You're still going to get 196 joules. Positive. Why? Because both gravity and, well, your gravity is contributing it to and going down the ramp, and it's moving down the ramp, right? So they're sort of working with each other. So you're going to gain kinetic energy, right? Follow? All right. So this works. There's absolutely nothing wrong with doing it that way. Oh, yeah, that's going to happen a lot. So, yeah. All right. I think it's instructive, though, to show this to you a different way. Remember, what I always find to be most beneficial is to think in terms of the components of either the force or the displacement. And for whatever reason, it always seems, I don't know, I guess it doesn't matter. I guess if you do components of the distance, then it's just force of gravity times 4, right? right? And then you get 196, right? Another way to think about it is this, though. Here's your box. My displacement is this way, right? So let's find our force of gravity parallel. Okay? So if we do that, that's going to be Fg times the sine of, I need to give these things names. Here. So we already called the 60 degrees theta, right? Let's call the 30 degrees, let's call that phi. All right, are we good? So, when I find my parallel component, am I going to use the 60 or the 30? The phi or the theta? The phi, right?
Why isn't it phi going from?
I don't know, it's a good question. I'll write the Greeks. Thank you, Mickey. I thought that joke was worth. I was happy with that one. All right. All right. I'm going to wake up at like 3 in the morning giggling about that. None of you thought it was funny. Except for me. All right. So look what happens. Our force of gravity is, it's 5 times 9.8, right? It's 5 times 9.8 times the sine of 30 degrees, right? Which is the same as the cosine of 60, right? So this ends up giving you 24.5 newtons. And then what's my displacement? 8 meters. So if you do work of gravity, that's going to be our Fg parallel times d. So it's 24.5 newtons pulling it in a direction parallel to d times 8 meters. And you still get 196.
That seems a lot more difficult.
But my point is that as long as you correctly either break your force or your displacement up into a component that's parallel with the other one, you can just straight out multiply. All right, are we good or no? Okay, cool. All right, now, work done by normal force. Don't shout it out. Everybody take a second and see if you can figure out what the work done by the normal force is. All right, I see some of you guys doing this. How come? Why, Mickey?
Because it's going down.
Tell me a little more.
It's not going up.
I have an answer.
Okay, what do you got, Alex?
Because the normal force doesn't like this makes it answer.
Okay, you're warmer. Warmer. Alex, what do you got?
He said it all.
Even if there was no friction. All right, Caitlin, what do you got? There you go. Look, you guys, the motion is this way. Shh, that's okay. The normal force is perpendicular to it. Okay, and so it's not contributing to the motion is correct, but mathematically it's because they're perpendicular. Is that what you're saying?
Well, it's not moving this way.
But even if the box was moving up the ramp, the normal force would still not do any work.
Because it's not moving downward.
Oh, you mean the normal force?
Yeah, the box is not moving downward.
Oh, I see. This way. I see. I just didn't understand. I thought you were pointing up the ramp. You're pointing this way.
I still don't understand.
I see. You're saying, I see what you're saying. There's,
The box is not moving off the ramp.
I understand. Now I agree with you.
Yeah.
Now I agree with you. Okay. In any case, the work done by the normal force is 0 because the displacement and the normal force are perpendicular. All right. Are there any forces in this example other than normal force and gravity?
No friction.
Yep, no friction.
Perfect.
So that's it, right? Oh, I forgot to write that in the problem. Okay, so our net work then should just be 196 joules. So if we start at rest, what's the kinetic energy at the bottom going to be? 196. So what's the velocity at the bottom? 8.85, the same thing we got before, right? All right. Oh, I forgot my joules. Alex, what's up?
The force, if there were friction, there would still be no work done by the force.
That's correct. But there would be work done by friction.
Oh, there would be.
Yeah.
Because like friction from normal force, right?
But they're different forces. So you would have to calculate work done by normal force, 0. Work done by friction, not 0. And then go from there. And we'll do problems like that. Just, yeah.
Technically, You say like perpendicular vectors don't affect each other, but technically doesn't normal force affect friction?
Yes.
But they're perpendicular.
Now, this is going to become a semantics argument.
Okay.
But it's not the normal force that's affecting the motion.
No,
The normal force creates friction, and then the friction affects the motion.
Incorrect.
So yeah.
But friction itself is affected by the amount of normal force.
I hear what you're saying, but if there was no friction, the normal force wouldn't matter. So,
Isn't
I-
friction determined by mass, and the normal force is just a way to use the mass in the equation?
no, because you can have mass but no normal force. It's still not a friction. Cool. All right, are we good? Alex, Alex, I understand what you're saying, but do you understand the essence of why I say that? Okay. All right. All right. Now. Shh. All right. So some of the problems in this chapter are really weird, and the reason they're set up this way is they want you to be familiar with this work energy theorem that we learned the other day, right? That the net work is equal to the change in kinetic energy. All right. So Roy's gonna lift this box onto a platform. We're gonna figure out how much work he did, but we're gonna do it in a real roundabout way. And I get that this is weird, but I really think that going about it this way is gonna, long run, it's gonna make things sort of gel together better. All right. So kind of bear with me here. All right. So. We're lifting a box up onto a platform. So the work done by gravity, well, that's just going to be the force of gravity, which is still 5 times 9.8. And then he's lifting it up, so the displacement's going to be positive 4 meters. Excuse me, that was gross. And you get negative 196 joules, right? Just like when we threw it up in the air, right? Follow? All right, so now we want to figure out how much work Roy did in lifting this thing. But the problem is we don't really know how much force he exerted, right? Now, you guys, how much force does he have to exert? Maybe we don't know this. So it weighs 5 kilograms, right? Or it has a mass of 5 kilograms. So the weight is 49 newtons, I think. So what's going to happen is, as he lifts it, assuming it starts and ends at rest, basically his average force is going to end up being 49 newtons. He has to exert a little bit more to get it moving, and then a little less to stop it. The little more at the beginning averages out with a little less at the top, and so the average force is 49 newtons. Okay? So hopefully the work that he will do will just be 49 times 4, or positive 196 newtons. Okay? But that might not be, but that's not how how we want to approach it at this point. All right? So we're going to use the work energy theorem. So if we assume that the box starts at rest, and then he's lifting it up onto a platform, so what's the ending kinetic energy going to be? Presumably 0, right? So what's the change in kinetic energy? 0, right? Even though it was moving in the interim, he did a little extra work to get it moving, but then he stops it at the top and takes that kinetic energy away again. Okay? So our change in kinetic energy during the trip of this box is 0, which means that the work net is 0. Well, what are the only two forces acting on the box? Roy and gravity. So this is equal to the work done by gravity plus the work done by Roy. Well, let's see. Our net work is 0. The work done by gravity is negative 196. So the work done by Roy has got to be 196, right? Does that make sense, you guys? So the idea is, if there wasn't gravity and Roy exerted 49 newtons on this thing, it would be accelerating very quickly, right? Okay? But what's happening is gravity kind of cancels out the kinetic energy it would have had, resulting in a net work, a change in kinetic energy of 0. Cool? All right. Now, if Roy lowered it, it would just be the opposite, right? He would be doing negative work, and gravity would be doing positive work. But again, they cancel out. I'm seeing some blank stares. Do you want me to run through that real quick?
Why would he be doing negative work?
Because when he lowers it, he's pushing up to prevent it from falling.
Oh, okay, that
which is wild, right? When you lower something, you're still pushing up, right? Right? Like think about what happened when you get in an elevator if it pushed you down, right? That'd be bad, right? Okay? It pushes you up, it just controls your fall, right? Okay? All right. Everybody good? All right. Very Wile E. Coyote, right? Okay. All right. I remember writing these notes and thinking, God, this is tedious. And, this is tedious. All right. So this one's basically going to amount to the same thing. This time he's using the ramp to push the block up. I don't know that we have to go through the calculations on this, but it's going to be the same thing, right? The idea is when he pushes the box up the ramp, he's going to exert a smaller force over a bigger distance. Okay? So again, the work done by Roy is still going to be 196 joules, right? But he's working against gravity, which is negative 196 joules. And so your net work still turns out to be 0. So this is basically just more of the same thing. Follow? You guys want me to run through the example? I'm happy to. Okay. All right. So, and then the last 4 slides here are just kind of concept-y questions. So I think we decided we were going to do all the concept-y questions on the next, the next, not work day, the next solutions day, right? So that was originally supposed to be tomorrow, but we just moved it to Thursday, right? Okay? All right. So I guess that's that. Man, I'm really unhappy with those notes. Yeah, there's not that much to it, so